Hello, Dr. Bone and Dr. Salvaganathapi. My name is Kenny, and along with my group members, Ernest, David, and Ravi, we would like to welcome you to our capstone presentation. Our project is the Automated Firewood Bundling System, and throughout this presentation, we will discuss our project objective, our overall design process, as well as our results and recommendations. The main objective of this project was to design and construct a prototype that has the ability of automating the firewood bundling process. Current firewood bundling processes are very labor intensive, and by automating this process, we will be removing the manual labor involved. Here's a list of our project deliverables. Our first deliverable was to define the problem, which included performing background research of existing firewood bundling processes, as well as identifying sub-objectives for the design. Our second deliverable was to create different initial design concepts. The idea was for each group member to develop one design that incorporated the components for each sub-objective. Our third deliverable was to select a final design, and this would be done by collectively as a group reviewing each initial design concept and selecting the best components from each to create the final design. Our fourth deliverable was to iterate and improve the final design, and this could be done through engineering analysis as well as testing. Our fifth deliverable was to construct and build the prototype. This would be a proof of concept prototype, which would showcase the completion of our sub-objectives. Deliverables 1, 2, 3, and 4 were completed. However, deliverable 5 was not. Our group was in the process of building our prototype. However, due to closure of the machine shop, we were unable to complete. Now, I would like to discuss the background of this project, which would answer the question, why bundle firewood automatically? The client for this project is FP Innovations, a research and development company within the Canadian lumber industry. Through their research, they have discovered that current firewood bundling processes are very labor intensive. Also, a shortage of labor in these remote areas where the lumber industry occurs creates a very big issue. With this in mind, our client has come to us for help in designing a device that can automatically bundle firewood. The device must also be robust and must be able to withstand harsh weather conditions since it will be operated in the outdoors. So the sub-objectives for our project. The goal of our system is to automatically, 1, accept the cut firewood pieces from an industrial log splitter at a convenient height. 2, orientate the firewood pieces into similar alignment and direction. 3, stack the firewood pieces into a 35-liter bundle, which was a constraint given by the client. 4, package the firewood. And 5, repeat the bundling process. After discussion with the client, we decided to remove sub-objectives 4 and 5 as the client decided that it was best for us to focus on the accepting, orientating, and stacking portions for this project. This was one of the major changes made to our project from the previous presentation.
Hi, my name is Ravi, and I'll be going through the mechanical design iterations, basically our journey through the design process. There were several changes and iterations made throughout the design process. However, there were 3 main designs that were created in the whole span of the project. The first design iteration involved the use of a vibration motor and a V-shaped hopper to funnel the firewood into a curved chute, and it would be aligned in this process. The firewood pieces would then get released into a bucket, and a strapping machine can bundle the wood together. The wood bundle would get ejected as seen in the second picture, and the process would continuously be repeated. The first design iteration involved some pros and cons. Some of the pros involved that it was a very simplistic design. It's a cheap orienting method because the vibration motors are relatively cheap, and there's only a few components. Some of the bigger cons was that the wood would most likely be jammed in the curved chute. The vibration motors would not be enough to manipulate the firewood, and there's no ability for the wood to be stopped when the strapping would occur. And lastly, the strapping machine is extremely expensive. As mentioned by my teammate Kenny, these were our project objectives. However, as you can see, objective number 4 was strike through because it was beyond the scope of the project. It's too expensive, and there's commercially available devices that can accomplish this task if the client is interested. Therefore, our project supervisor said to focus on the first 3 objectives instead. The second design iteration involved the use of chains instead of the vibration motor to allow for the firewood pieces to be funneled inside the chute. The chute has a slanted geometry to prevent firewood pieces from getting jammed, and at the end there's a little vertical section that allows for pieces to fall in vertically. And there's flaps on the bottom of the chute to open and close as required for strapping purposes. The second design iteration also had some pros and cons. The pros said that it's a very rigid and strong design, and the flaps at the bottom can be used to control the flow of wood. The cons involved the use of pneumatics because they are a really complicated system, and implementing them would be extremely expensive and complicated. the capacity of holding firewood would be limited. The wood pieces could get jammed in the chains of the conveyor, and they could get shredded by the conveyor as well. And lastly, it requires a complex structure to mount the conveyor system as well.
Hello, my name's David. I am going to be talking about our final design. So from those design iterations that we talked about previously, there was still a little bit of work that needed to be put into them in order to create something that would have been a viable prototype. So this section is how we took advice from our advisor, the technicians, put together our own ideas, and developed a design for each part of the system. So for the design of the conveyor, we decided to switch away from chain drives to belts. Reason for this change was because we felt that chain drives would cause more jamming of the wood, and the wood would get jammed in and it would start to shred the wood. And we also had a discussion with our client about this design, and they agreed that belts are more common for transporting wood than chains are. We also decided to move the conveyor to a horizontal configuration instead of on an angle. And the reason for this was it would make it a lot easier to mount the hopper and also create a support structure, as well as by making a bigger hopper, we can accommodate a larger volume of wood. Additionally, in order to figure out the sizing of the conveyor, we decided to make a 1-for-1 scale model on a whiteboard, and we used actual firewood, held it up to try to figure out what the ideal lengths were. We ended up deciding on 8-inch wide conveyors with a 9-inch gap in the center. So the two alternating conveyors will drop a piece of wood down the center, and that will restrict the wood to the XZ plane. Here you can see a CAD model render of the conveyor that our team designed. On the left-hand side picture, our conveyor uses 3-inch wide steel bars as the sidewalls, and then they're separated using 1-inch square tubing cut to 8.5 inches in length. 8.5 inches in length was chosen because our belt that we decided on was 8 inches wide, and that'll give us a 1/4 inch of clearance on each side so it's not rubbing up against the walls. Moving on to the center picture, welded onto those spacers we have a support plate. This support plate is just sheet metal that is going to be welded on in order to make sure that the wood, when it falls onto the conveyor, it does not puncture the conveyor belt, and it also stays supported on the conveyor. In the bottom right of the center picture, you can see we have a tensioning mechanism. So this is in order to make sure that the conveyor belt that we fit on top is tight and it rolls effectively without slipping. And then finally, in order to accommodate the conveyor belt that we chose, we needed a 3-inch OD roller. So in order to create that, we used 3/4 inch steel rod as a shaft, and we machined down the ends so that they could go into the bearings as well as get mounted onto the motor. Then from that, we machined a couple plates that we press fitted onto the shaft, and then a 3-inch OD steel drum on the outside was also cut and welded together. Moving on to the design of the hopper. So the purpose of the hopper is to be able to catch the firewood that gets deposited off of the conveyor coming up from the truck. So we wanted to be able to hold a large amount of firewood, but not too much. So we had to decide on how large to build this. Well, we went to a similar method to how we did design the size of the conveyors. We drew it on a whiteboard, a 1-for-1 scale model. We held up some wood to it to decide what the appropriate size was, depending on how much volume we wanted to hold. So again, we switched to flat conveyors, and this time we used an angled hopper on all 4 walls. The reason for this is because we wouldn't want a conveyor going in to a flat surface, because that would just lead to a lot more jamming. We wanted it to be open on all sides to be able to encourage more wood flow, because the more the wood is flowing in that hopper, the easier it is for those conveyors to move it around and have it fall down the center and get oriented. So the design of this hopper increased the capacity that was able to be held, the capacity of wood that was able to be held from design iteration 2. And it was also beneficial because it's very simple design, easy to build, and easy to manufacture. And here we have a CAD model render of the hopper. We also decided to include in this picture the conveyor belts that the hopper is going to sit on. So this will be fastened to those conveyor belts as such. And you can see through the picture on the left that the opening of the hopper does not cover the entire length of the conveyor. The reason for this was, one, because we could get a lot more standard sizing of both conveyor belts and steel using a slightly larger conveyor, but also we don't want part of the opening to be in the curved edge of the conveyor, because then it's much more possible for smaller pieces of wood to get jammed underneath. We don't want that, so we decided to keep it away from the ends a little bit. And then from the picture on the right, you can kind of get an idea where if wood was touching both sides of the conveyors, how the conveyors moving in opposite directions would help turn that piece of wood into the proper plane where it can fall down. Moving on to the design of the chute. The chute is one of the most critical parts of our entire design. One of the biggest issues that we realized very quickly when dealing with firewood is how difficult it would be to avoid the idea of jamming. Wood is very obscure in shape and size. There's so many variables when dealing with wood that it's hard to consistently orient wood without having it jam up. So we tried to brainstorm a lot of ideas to prevent this jamming. We ended up deciding on a chute because it would restrict the wood to a uniaxial direction. Like we said before, the two conveyors will drop the piece of wood down, but that only restricts it to a planar direction. We wouldn't want it to drop straight vertical, because then that would jam up other potential chutes that we have. So the way that we designed this chute is that when the wood piece drops, it's going to orient itself into a uniaxial direction and slide down the chute. We wanted to make sure that this was a viable design, so we built cheap wooden prototypes to test this theory, and those videos are going to be on the next slide. So we ended up testing a lot of pieces of wood, and for the most part, this actually worked out very well. Unfortunately, there were a few issues that we needed to address. So on the left-hand side, we showed this video to highlight that pieces didn't always fall off the edge level. They would come off the edge of the chute and they would angle downward. So in order to rectify this, we decided to add spring-loaded flaps on the ends, which we simulated in the second video holding the clipboards. So this really helped fix that issue. But then one of the issues we also highlighted in the second video was that the chute was too wide and pieces were able to turn. Now we didn't want to just narrow down the chute because some pieces, like we said, firewood is very variant, and we wouldn't want larger pieces to then get stuck. So instead what we decided to do is we decided to make a V shape in the bottom of that last little bit to help keep the pieces of wood center. And here you can see a CAD model render of the design of our chute for our proof of concept prototype. Now, again, I want to reiterate that this prototype that we are building is a proof of concept design, and we said earlier that this is going to be used up north and therefore must be able to withstand the elements. This is just a cost-effective design to prove that the idea is worth pursuing. So that's why we're making it out of wood. So the white wood on the chute is melamine wood, melamine coated wood, so that the wood will slide a lot easier. As you can see on that third section of melamine, it's tapered into a V shape, and there's also a slot down the middle. So the reason for the V shape is, like we just showed in the previous video, to make sure that the wood doesn't move as it's going down the chute. It helps keep it in its center. And also the reason for the slot is so that any debris can fall down and it won't interrupt and jam up the chute. After finishing the design of the proof of concept prototype, we then need to decide how to power the prototype. So in order to drive the conveyors, we decided on these high torque, low speed motors so that we could avoid having to design an expensive gearbox in order to change the gear ratio with some more high speed motors. This is also powered using a 12-volt DC source, which is easy to move around to a remote location. And it's driven using worm gears inside the motor, as you can see in the picture on the bottom left. This motor rotates at about 45 RPM, and the slow speed means that the motors will have sufficient torque to rotate the conveyor even with firewood pieces stacked on top of it. So here's a circuit diagram for the system that we'll be using to power these motors. So it's going to be powered using a 12-volt battery, and that's going to power both motors. There's going to be two 30-amp fuses, one on each run in series in order to work for one motor each. We will also have toggle switches to be able to turn on and off the motors in order to simulate a control system. Of course, there will be no control system in the proof of concept prototype due to cost reasons, but we will be turning them on and off as such. And the reason for this design is it's aimed to have a low cost. So these motors were actually sourced through one of the group members who had them. They were able to obtain them from the robotics club from their high school. So we were able to save a lot of money on the motors. Now, after putting all these components together, you can see we came up with our final prototype design. Now, keeping in mind that this was a very cost-effective model that was constructed of cheap materials such as wood in order to be a proof of concept design. So this wouldn't be the model that would be used by FP Innovations up north. They would require a much more robust model using weather-resistant materials. However, upon verification of the system's effectiveness, a more robust prototype would then be designed and hopefully built.
Hi, my name is Ernest Lee, and I will be talking about a prototype. So essentially what our team has accomplished so far in terms of constructing a physical prototype, and although we do not have a finished product ready before COVID-19 causes school to close, I will go over what we have completed so far. The team was successfully able to construct a wooden prototype early on, as you can see on the right side of the slide. This was primarily used to test the feasibility of the design, along with to determine the best angle configuration for the chute, so that the wood is able to slide to the end of the chute at perfect velocity, along with to seek any improvements that could be made to the chute design. The team was able to iterate through the conveyor belt design several times to refine it, to make it most cost effective as possible, and to keep the number of parts in the conveyor assembly to a minimum for efficient manufacturing. All the parts in the conveyor were able to be machined, and the next steps to this conveyor assembly would be to weld all the parts together and mate it to the motor to be able to physically test it. So unfortunately, the team was cut short of prototype construction, and the following items are what is left to be completed to be able to finish the prototype. So first off, we need to machine a keyway on the conveyor shaft using a mill for the motor to be attached to the conveyor. Secondly, the machine conveyor parts would need to be all completely welded together. Third, the motors would need to be attached to the conveyor, and a circuit would need to be created to be able to allow the motors to run. Fourth, the hopper pieces would need to be cut from plywood and put together. Fifth, the hopper needs to be attached to conveyors, and the support structure would need to be welded together for the prototype. Sixth, the flaps would need to be added onto the chute, and all the different parts of the prototype, including the conveyors, the hopper, and the chute, would all need to be assembled together. And lastly, the system would need to be tested, and it would also need to be fine-tuned. So the team ended up spending a total of $686.48 on the materials for the prototype, and the costs are divided among four major categories, which are broken down in the table you can see on the slide. So firstly, the team spent $393 on metal for the support structure and the conveyor, and this was purchased at the metal supermarket supplier. Secondly, the team spent $59.47 on wood for the chute and the hopper, and this was purchased at Atkinson Lumber. And thirdly, the custom rubber belts were purchased for a total price of $196.92 at New Tech Conveyor Belts Limited. And lastly, the miscellaneous parts such as screws, nuts, and bearings totaled to an amount of $37.09, causing our total amount to be $686.48. So throughout the course of this project, our group also focused on several sustainability aspects as well. So the first one is social sustainability. And our project automates the firewood bundling process, effectively eliminating heavy lifting and repetitive motions that are needed to be done by lumber workers. And this ultimately would be able to reduce the safety hazards and injuries caused in the workplace. Secondly, our product also makes a tremendous environmental impact as well. There are no greenhouse gases produced by our product, keeping our emissions to a minimum. And this is done by the group selecting and using electric motors instead of gasoline or diesel powered motors, which produces no greenhouse gases. And lastly, our product also makes a huge economic impact. Not only does it streamline the firewood bundling process, making it cheaper and easier, it also opens up more than 50 jobs for the design, the production, and manufacturing of this actual firewood bundling product. Moving on, we can talk about the final thoughts of our project. So what's next and what happens after we finish our prototype? Recommendations for a real system include using stainless steel material for the entire design instead of using wood, since it's more weatherproof and robust. As well, a overlying well-designed control system can be developed where it's able to detect when the bucket below the chute is full, disengage the conveyors and initiate the bundling process and repeat the whole thing again would be beneficial. Additionally, sensors that can be added on the chute to detect and stop the machine when there are jams would be helpful as well. And more safety functions can be implemented in our prototype and our design as well, such as emergency stop buttons and warning labels. As well, the use of more than one conveyor system and chute could be implemented if the sorting process is slow. And lastly, any other improvements that are observed when we are testing the physical prototype could be made, since there would be a lot of different changes when that occurs. So some future projects that can stem off our current project are, I guess there's two main ones. So the first one is the transport of the finished bundle. So creating a project that is able to transport the bundled firewood directly onto a truck. And secondly is a custom strapping slash bundling machine to retrofit this project. So our current design makes use of a industrial, commercially available strapping machine, and perhaps creating a custom strapping or bundling machine for this specific application would be more cost effective and efficient for our product overall. So these are two considerations for future products or projects that stem off our current project.